Hi! In this video, we delve into the fascinating world of gravitational waves, a phenomena predicted by Einstein's theory of general relativity. In this video, we'll discuss about gravitational waves and their significance in astrophysics. So join us as we unravel the secrets of these cosmic ripples and discover the groundbreaking implications they have for our understanding of the universe. From black holes to neutron stars, get ready to dive into the mind-bending world of gravitational waves. Let's begin. Gravitational waves are oscillations of the gravitational field that travel through space at the speed of light. They are generated by the relative motion of massive objects. They were first proposed by Oliver Heaviside in 1893 and then later by Henry Poincaré in 1905 as the gravitational equivalent of electromagnetic waves. In the year 1916, Albert Einstein demonstrated that gravitational waves are ripples in space-time, well explained by his general theory of relativity. Gravitational waves transport energy as gravitational radiation, a form of energy similar to electromagnetic radiation. In Einstein's general theory of relativity, gravity is treated as a phenomena resulting from the curvature of space-time. This curvature is caused by the presence of mass. If the masses accelerate, the curvature of space-time changes. If the motion is not spherically symmetric, it will cause gravitational waves which propagate at the speed of light. For instance, if you start dancing with your friend right now, the two of you will produce gravitational waves. However, those gravitational fluctuations will be so tiny that it will be very difficult to detect them. As a gravitational wave passes an observer, that observer notices distortions in the space-time. It will either contract or expand. Distances between objects increase and decrease rhythmically with the same frequency as that of the passing gravitational wave. The magnitude of this effect is inversely proportional to the distance from the source. Note, it is the distance and not the distance squared. Gravitational waves which can be observed therefore require very massive objects moving very fast. This happens, for instance, in the case of in-spiraling binary neutron stars. But since they are very far away from us, the effect when measured on Earth is very small, even less than 1 part in 1020. For example, the waves given off by the final merger of binary black holes named GW150914, the first gravitational wave signal ever detected, reached Earth after traveling over 1 billion light years as a ripple in space-time that changed the length of the 4-kilometer-long arm of the LIGO detector by 1,000th of the width of a proton. This is proportionally equivalent to changing the distance to the nearest star outside the solar system by 1 hair's width. This tiny effect from even extreme gravitational waves makes them observable on Earth only with the most sophisticated detectors. Gravitational waves do not strongly interact with matter in the way electromagnetic radiation does. This allows astronomers to observe events involving massive exotic objects such as black holes and neutron stars in the distant universe that cannot be observed with more traditional means such as optical or radio telescopes. Due to the weak coupling of gravity to matter, gravitational waves experience very little absorption or scattering even as they travel over astronomical distances. In particular, gravitational waves are expected to be unaffected by the opacity of the very early universe, which means that even when light could not travel freely in the dense early universe, gravitational waves could. And therefore, gravitational wave astronomy is a unique window into the distant universe. In principle, gravitational waves can have any frequency. But very low frequency waves can be detected using pulsar timing arrays. In this technique, the timing of approximately 100 pulsars spread widely across our galaxy is monitored over the course of years. Detectable changes in the arrival time of their signals can result from passing gravitational waves generated by merging supermassive black holes. These changes in timings can be used to locate the source of the waves. Using this technique, astronomers have discovered various supermassive black hole mergers occurring in the universe. Stephen Hawking and Werner Israel list different frequency bands for gravitational waves which could plausibly be detected, ranging from 10 to the power minus 7 Hz to 10 to the power 11 Hz. The difficulty in directly detecting gravitational waves means it is also difficult for a single detector to identify by itself the direction of the source. Therefore, multiple detectors are used to distinguish signals from other noise by confirming that the signal does not originate on Earth and to determine the direction by means of triangulation. This technique uses the fact that the waves travel at the speed of light and will reach different detectors at different times depending on the direction of the source. Although the differences in arrival time may be just a few milliseconds, it is sufficient to identify the direction of the origin of the wave with considerable precision. In the case of the source GW170814, for instance, 3 detectors were operating at the time of the event. Therefore, the direction is precisely defined. The detection by all 3 instruments led to a very accurate estimate of the position of the source with a 90% credible region of just 60 square degrees, a factor 20 more accurate than before. The speed of gravitational waves in the general theory of relativity is equal to the speed of light in vacuum. In the theory of special relativity, the constant c not just represents light. Instead, it is the highest possible speed for any interaction in nature. Coming to think of it, c is a convergent factor for changing the unit of time to the unit of space. This makes it the only speed which does not depend either on the motion of an observer or a source of light or gravity. That is why the gravitational waves move with the speed of light, which is also the speed of any massless particle, such as gluons, which are the carriers of strong force, photons, which are the carriers of electromagnetic energy, and the hypothetical gravitons associated with the gravitational waves. In general terms, gravitational waves are radiated by large coherent motions of large mass, especially in regions where gravity is so strong that the Newtonian gravity begins to fail. But note that the effect does not occur in a purely spherically symmetric system. A simple example of this principle is a spinning dumbbell. If the dumbbell spins around its axis of symmetry, it will not radiate gravitational waves. But if it tumbles end over end, as is the case of 2 planets orbiting each other, it will radiate gravitational waves. The heavier the dumbbell and the faster it tumbles, the greater is the gravitational radiation it gives off. In an extreme case, such as when 2 weights of the dumbbell are massive objects like neutron stars or black holes orbiting each other very quickly, significant amounts of gravitational radiation would be given off. By the way, do check out our earlier videos on black holes and neutron stars if you haven't done so already. Water waves, sound waves, and electromagnetic waves carry energy, momentum, and angular momentum away from the source. Gravitational waves perform the same function. For example, a binary system loses angular momentum as the 2 orbiting objects spiral towards each other. The angular momentum is radiated away by the gravitational waves. The waves can also carry off linear momentum, a possibility that has some very interesting implications in astrophysics. After 2 supermassive black holes merge, emission of linear momentum can produce a kick with amplitude as large as 4,000 kilometers per second. This is fast enough to eject the resultant black hole completely from its host galaxy. But if the kick is too small to eject the black hole completely, it can still remove it temporarily from the nucleus of the galaxy, such that it then begins to oscillate around the center, eventually coming to rest. A kicked black hole can also carry a star cluster with it, forming a hypercompact stellar system. Or it may carry some gas, allowing the recoiling black hole to appear temporarily as a naked quasar. For example, the quasar SDSS J0927 plus 2943 is believed to host a recoiling supermassive black hole. Even though Einstein predicted the existence of gravitational waves in 1916, the first proof of their existence didn't arrive until 1974. In that year, two astronomers, Russell Hulse and Joseph Taylor, used the Arecibo radio observatory to discover a binary pulsar 21,000 light years away from Earth. This was exactly the type of system that general relativity predicted should radiate gravitational waves. Knowing that the system could be studied to test Einstein's prediction, Taylor and his two colleagues, Joel Weisberg and Lee Fowler, began tracking the radio emissions from the stars to measure how their orbital period changed over time. After just 4 years, they first reported seeing a change in the period that verified that the stars were getting closer to each other at the rate predicted by general relativity. In 1993, Hulse and Taylor were awarded the Nobel Prize in Physics for their discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation. But even so, inferring the existence of gravitational waves via studies of pulsars remains an indirect evidence for their existence. But all of this changed on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, physically sensed the undulations in space-time caused by gravitational waves generated by two colliding black holes 1.3 billion light-years away from Earth. This was a historical moment for all of humanity. LIGO was designed to make inconceivable, exquisitely small measurements observed billions of light years away from the source of gravitational waves. At their core, the LIGO detectors are Michelson interferometers, conceptually similar to the sort of device that was invented in the 1880s. They are similar because just like a Michelson interferometer, the LIGO detectors are L-shaped with two arms equal in length. A mirror at the vertex of the arms splits a single light beam into two, directing each beam down an arm of the instrument. The mirrors at the ends of the arms reflect the beams back to their original point, where they are recombined to create an interference pattern called fringes. But this is where the similarities end. The LIGO's interferometers are far larger and much more complex than the builders of the world's first interferometers could have imagined. Besides their scale, one of the major differences between the original Michelson interferometer and LIGO is that LIGO uses a laser beam as its light source, whereas the first Michelson interferometer used a plain white light source. With 4 kilometers long arms, LIGO's interferometers are by far the largest ever built. The scale of LIGO's instruments is crucial to the search for gravitational waves. The longer the arms of an interferometer, the smaller the measurements they can make. And having to measure a change in distance 1,000 times smaller than a proton means that LIGO has to be larger and more sensitive than any interferometer ever constructed before. While 4-kilometer long arms already seems enormous, if LIGO's interferometers were simple Michelson interferometers, they would still be too short to enable the detection of gravitational waves. But there are practical limitations to building a precision instrument much larger than 4 kilometers. So how did LIGO possibly detect gravitational waves? Well, the paradox was solved by altering the design of the Michelson interferometer to include something called Fabry-Perot cavities. This figure shows the modification to the basic design. An additional mirror is placed in each arm near the beam splitter and 4 kilometers from the mirror at the end of that arm. This 4-kilometer long space constitutes the Fabry-Perot cavity. After entering the instrument via the beam splitter, the laser in each arm bounces between these two mirrors about 300 times before merging with the beam from the other arm. These reflections serve two functions. First, it builds up the laser light within the interferometer, which increases LIGO's sensitivity. In other words, more photons are keeping track of the length of the arm makes LIGO more sensitive. Secondly, it increases the effective distance traveled by each laser from 4 kilometers to about 1200 kilometers. This is crucial because the longer the interferometer's arms, the bigger the absolute changes that gravitational waves make to total arm length. In this case, the total distance traveled by the lasers. Consequently, the longer the arms and the farther the lasers travel, the bigger is the effect even small gravitational waves have on the whole interferometer, making them more readily detectable by this very sensitive instrument. But length is not the only limiting factor in LIGO's sensitivity. Laser power is also a consideration. Just as increasing length increases the interferometer's sensitivity to more distant gravitational waves, increasing laser power also enhances its performance. In this case, the more laser photons that merge from each arm, the sharper will be the fringes that are measured by the photodetector. But there is a problem here too. LIGO's laser first enters the interferometer with the power of about 40 watts, but it needs to operate closer to 750 kilowatts to have any hope of detecting gravitational waves. Here we have another paradox. Just as it would be impossible to build a 1200 kilometer long interferometer, building a laser with this initial power is very difficult. Once again, LIGO uses mirrors to solve this dilemma using a technique called power recycling mirrors. Inside the interferometer, light from the laser passes through the transparent side of a power recycling mirror to the beam splitter where it is directed down the arm of the interferometer. The instrument's alignment and mirror coatings and even quantum mechanics ensures that nearly all the laser light entering the arms follows a path back to the reflective side of the power recycling mirror before it exits the photodetector. As laser power is constantly entering the interferometer from the laser itself, the power recycling mirror continually reflects the laser light that has already traveled through the instrument back into the interferometer, hence the term recycling. This process greatly boosts the power of laser light stored inside the Fabry-Perot cavities without the need to generate such a powerful laser beam at the start. The boost in power generated by power recycling results in a sharpening of the interference fringe that appears when the two beams are superimposed. Fringes which will tell scientists if a gravitational wave has passed. The sharper the fringes, the easier it becomes to identify the telltale signs of gravitational waves. Besides these, LIGO's interferometers were constructed with extraordinary mechanisms to damp out unwanted vibrations or noise, making it easier for the instrument to sense just the vibrations caused by gravitational waves. And just so that you know, with all these modifications, LIGO's interferometers are more precisely known as a dual recycled Fabry-Perot-Michelson interferometers. With the state-of-the-art technology in place and better detectors under construction, scientists have now demonstrated the existence of gravitational waves with highly sensitive detectors at multiple observation facilities. As of 2012, the LIGO and Virgo observatories were the most sensitive detectors operating at resolutions of about 1 part in 5 times 1022. The Japanese detector Kagra was completed in 2019 and reported its first joint detection with LIGO and Virgo in 2021. The European ground-based Einstein telescope is under development. A space-based observatory named the Laser Interferometer Space Antenna, or LISA, is also being developed by the European Space Agency. In August 2017, the LIGO and Virgo detectors received a gravitational wave signal from a source now named GW 170817 at nearly the same time as gamma-ray satellites and optical telescopes received signals from its source in galaxy NGC 4993 around 130 million light-years away from Earth. This measurement constrained the experimental differences between the speed of gravitational waves and light to be smaller than 1 part in 10 to the power minus 15. As we continue to study gravitational waves, we are also learning about the extreme cosmic events that produce them. The implications of gravitational wave detection are far-reaching, with the potential to revolutionize our understanding of the universe. By analyzing the data from gravitational wave detections, scientists can gain insights into the properties of black holes and other cosmic phenomena. Gravitational waves have significant implications for our understanding of the cosmos, and their discovery has marked a new era in astrophysics. I really hope you enjoyed this short discussion on gravitational waves. We will soon discuss them in greater technical details. If you like this video, please do share, subscribe, and like our channel, and share our content with other astronomy enthusiasts. I will see you next week. Until then, take care.